Welcome to another Druid Summit session. This one is called Load Drop Kill. This is a session that we did last year about the Druid segment lifecycle and retention rules and how to configure all that and how it works. But this one's a little different because a year has passed and now Druid 27 and Druid 28 are out and they bring more functionality. So it's actually now more like load, don't drop, then kill. Anyway, my name is Sergio Farragut. I am a senior developer advocate here at Imply. I've got 25 years in data analytics. I've built data warehouses. I've worked with HTAP databases, done a bunch of different things that you see here on the screen. I guess you can call me a jack of all traits and master of none. But the general vein of my career with distributed systems has been understanding the technology and understanding how to get the best out of it, both from a data modeling perspective and a query perspective. So with that, today we're going to talk about multiple historical tiers and how you use retention rules to use multiple historical tiers. And then we'll talk about the full life cycle of a segment. So let's talk about multiple tiers. Multiple tiers allow you to define different sets of historicals that have different characteristics. So you may have a set of historical nodes that have a lower cost in general because they're less CPUs, there's less memory, they use hard drives, maybe high storage, hard drives that ultimately give you a ratio of power to storage that is lower than the hot tier. In the hot tier, you have larger servers with more CPUs, more memory, more likely SSDs with less storage. So there's faster I/O. There's more power for each for the amount of storage available. So these provide faster queries. So the coordinator manages segment distribution, and the way it does this, it looks at deep storage, it looks at all the ingested segments that are marked as used, reads the retention rules associated to the data sources and to the cluster, and then executes multiple operations, right? It tells the historical nodes in different tiers to load copies of the segments, so to cache them for query purposes. It tells them to also unload them when they become unused or when they need to move from one tier to another. It marks them as unused when they're dropped from the cluster, and it also manages the cleanup, right? The kill operation, which deletes the unused segments from deep storage. So the way it does this is it looks at all of the segments that have been ingested into deep storage. And for each segment, it will apply first the data source specific rules, which, there could be multiple rules for the data source. So it'll apply those first. And then if there are no data source rules or none of those data source specific rules match, it uses the cluster rules. So what are these rules? Before what are these rules, let's talk about what are these rules and how to configure them. First, how to configure them. So configuring retention rules is done from the data sources view in the Druid console. You'll see within each row that represents a data source, there's a column called retention, and you can see the summary of the rule there. In this case, this table has a cluster default rule, but that small pencil there allows you to edit the retention rules for a particular data source. And that brings up this screen where you set up a set of rules. The order of the rules are important, so it'll read through for each segment. It'll try to apply each rule. If the rule matches, it will apply that rule. If not, it'll check the next rule. So the order is important. You'll want to have a forever rule. In most cases, associated to your data source, because that'll catch the bottom of the rules. If you don't have a forever rule at the end, it'll fall through to the cluster defaults and apply the cluster defaults at that point. Also, to edit the cluster defaults, there's this little edit button in the data source retention rules window. This link takes you to a very similar window, but where you're editing the cluster defaults. You can also set the rules through an API. There's a post request to the Druid Coordinator v1 rules endpoint with a data source name, or if you use the underscore default, you're changing the default for the cluster. And the payload is the set of rules, where each JSON object in this array is one of the rules, and they are shown in order, right? So this one's saying load by period to the hot tier, 2 copies for the period of 1 month. The second rule is load by period for the 12 months into the cold tier with 2 copies. And then this one's new. In Druid 27, we introduced a query from deep storage. So in order to keep segments around in deep storage, or to tell Druid when to keep them around in deep storage, you add a retention rule where the tiered replicants list is empty. So that indicates that you don't want the segments to be cached in any historical, but they will be kept for whatever the period defined here is in deep storage. So they won't be killed. They won't fall to the next rule, which would be the drop forever, that ends up removing the segments. So this allows you to configure how much data you're keeping in deep storage beyond what you're caching in the historicals. So let's talk about the rules in general. So the rules have a rule type and then followed by a time frame, right? So you'll see rule type forever, rule type by period. There's the drop before by period, which is a specific one that only exists for drop, and then rule type by interval. So if you look to the right, the forever one, well, it just matches any segment, right? So a segment has a time frame, so a start and an end to the data that it covers. So if the segment overlaps the rule, it will match the rule. So in the case of forever, any segment matches a forever rule. In the case of by period, you define the length of the period. So like in the example we had before, we had P1M, which means 1 month. And you can say include future or not. So you can say whether you want to also cover any segments that have timestamps in the future. So if the segment that we're testing against overlaps in any, even a little bit with the period expressed in green, so the period that you're defining, the rule will match. In the drop before period is a specific one where you're selecting to drop before so it's the opposite of the by period, but it's only usable for drops. Again, if it matches the green area, right, from a timeline perspective, it will be dropped. And then by interval, where you have static intervals, where you specify, the area that matches, or the portion of the timeline that matches is defined by a start and an end. So if the start and end of the rule match or overlap in any way with the start and end of the segment, it'll match the rule. Right, so with that, let's talk about the different types of rules. Load rules. So load rules do what they say. They load copies of the segments that match into different tiers. You can specify multiple tiers in the rule. This one just specifies 1 tier. But so this rule is saying load for a period of 2 months. Load that's the most recent period of 2 months up to now. Will load into the hot tier, and it'll load 2 copies of the segments into the hot tier. The drop rules for any segments that match will mark the segments as unused, and we'll see that segments that are marked as unused are the ones that are then cleaned up by a kill rule. Broadcast rules will broadcast the segment to all historicals, all brokers, and all indexers. So anyway, how does this work? The coordinator runs in cycles, right? The cycles are defined by the Druid Coordinator period parameter. That means that it's usually set to 1 minute. That means that every minute the coordinator wakes up and tries to do all of this work. And what it does is it reads the segment metadata from the metadata database. And for all the segments that are used, so the ones that have been ingested and are marked as used, and it also reads the current retention rules for all of the data sources and for the cluster. So then for each segment, it does the rule matching, finds the desired state. So how many replicas for each tier available are needed. It compares that to the current state, and then it issues commands to the historicals to either load segments or drop segments to achieve the desired state. It also does segment balancing by tier. So within each tier, it picks segments to move. So that what this does is the historicals end up using a certain amount of their space based on the original distribution of segments. And so that can get unbalanced, right? There can be historicals that end up having more segments than others. So this segment balancing process is continuously looking at that imbalance and telling historicals to load segments and drop segments to balance out the number of segments that each historical has. There's a set of parameters that control this process. The replication throttle limit there at the bottom controls the maximum number of segments to replicate. So that's replication specific to replication. New segments are treated differently. New segments are prioritized. So whenever there's a new segment ingested, it will always be prioritized over replication. Max segments to move is about balancing, so it's how many segments you want to move per cycle for balancing purposes. And on the top right, we have the historical parameter that is the num-loading threads. It defaults to the 1/6 of the number of cores. But you can grow the value if you need to load segments faster. So this is the number of threads that are downloading segments from deep storage and into each of the historicals. And at the bottom, we have the max segments in node loading queue. This is the depth of the load queue that each historical keeps. The maximum number of instructions that they're going to have to work off of. Now, this is how Druid works up to 27 in general, and in general, it's still the same behavior. But with Druid 28, there's the introduction of what we call smart segment loading. And this is going to be on by default when you install Druid 28. So you can turn it off if you want to, but it seems to be having much better behavior. It's sort of automatically tuning many of these parameters. So it automatically tunes the replication throttle limit, the max segments to move, the max segments in the node loading queue is actually unlimited now when you turn this on. And it also affects other things about segment loading, like using round-robin segment assignment. That's new segments are assigned in a round-robin fashion among the historicals within a tier. That's just a fast way of getting even distribution of segments. The replicant lifetime is set to 60. This means 60 cycles of the coordinator, which is, if it's 1 minute, that means an hour. This means that because the max segments to load is now set to unlimited, this will alert if after 60 cycles, so if after an hour, a particular load instruction has not been completed. It generates alerts. And the balancer compute threads is also now being calculated automatically to give the cluster, the coordinator, more resources to calculate the balancing algorithm that it uses. So the coordinator kill task is the other task that the coordinator runs. It also has its own period, right? It runs usually once a day. I'm not sure if this default has changed, but in the past, the Druid coordinator kill.on property defaults to false, which means you're not removing any segments. You probably want to set that to true so that when segments are marked as unused, they get cleaned up from deep storage and from the metadata database. So now let's talk about the life cycle of a segment given a set of rules. Right, let's set up a set of rules that uses all the tiers, right? We have a 1 month plus future into the hot tier as our first rule, then another 12 months for the cold tier. It's actually not another 12 months, right? It's a total of 12 months up to now. So if the first rule matches 1 month and the second rule matches 12 months, that means that segments are going to stay for 1 month in the hot tier and then migrate to the cold tier for 11 months. And then the next rule is the one we're specifying just deep storage. We don't specify a tier. That was introduced in 27. And in this case, we're saying 24 months. So in general, we're saying we're keeping 1 month in the hot tier, the next 11 months in the cold tier, and the next 12 months only in deep storage. Now, deep storage always has all of the segments, right? So it's going to have the 24 months worth of segments. And then a drop rule so that after the segments age beyond 24 months, we'll get rid of the segments. So with that, we'll set up, the cold tier, the hot tier, and the real-time task will cover a year's worth of data. And the native engine will have access to all of those. The native engine only queries historicals and real-time tasks. So anything that's not cached in the historicals is not visible to the native engine. So you define the time frame for which you want fast queries and you cache all of those segments. And then you have another time frame that allows you to have more older data still in deep storage and still queryable. But for that, you need to use the multi-stage query engine with the feature of querying from deep storage. Multi-stage query engine reads the segments directly from deep storage. So it has the full 12 months in this case available to it. And new to Druid 28, the query from deep storage also reads from the real-time tasks. So queries from using the multi-stage query engine will cover the full time frame, right? Everything that's in deep storage plus everything that is currently being ingested in real-time tasks. So let's take a look at, based on that example, what would happen to the segments. So a new segment is ingested, right, and produced in the indexers, and when it's finalized, it's published to deep storage. That gives us our golden copy of the segment, and the coordinator kicks in, sees the new segment. At this point, that segment is queryable directly from deep storage if you have Druid 27 or newer. And the coordinator is going to kick in and say that this is a new segment. It falls within the 1 month where we want 2 replicas in the hot tier. So it's going to create those load instructions in 2 different historicals, load those 2 segments into the hot tier. Time passes, a month passes, and the second rule kicks in, right? So now the coordinator is going to ask the cold tier to load at least 1 copy of the segment first, and then start offloading segments from the hot tier as it detects them as over-replicated. It does this 1 at a time, so it'll be 1 in the cold tier, and then remove 1 from the hot tier, add another 1 to the cold tier, and then remove another 1 from the hot tier, so you don't have over-replication. After this, so queries now are for this segment are running in the cold tier or through a query from deep storage that also see this segment. A year passes, and now they're considered over-replicated. They're still available in deep storage. They're still queryable from deep storage at this stage. And another year passes, and now we want to drop it, right? So at that stage, we'll end up removing it from deep storage, and it won't be queryable anymore from MSQ either. So that's sort of the whole life cycle given that set of rules. Another concept to talk about is availability zones and how that behaves for higher availability, right? So typically you'll have subsets of historicals within a tier assigned to different availability zones. You could also think of this as different racks, that have different power and maybe different disk array. So that if the disk array fails or if the power fails on that particular rack or on that availability zone, you'll end up with a failure and you'll need to use the other availability zones. Now, those of you who are thinking ahead see a problem here, right? If we lose availability zone 1, and the coordinator had decided to use historicals 1 and 2 for the 2 copies, then we've lost that segment. What'll happen is it's not disastrous. The coordinator recovers from this, but while it recovers, that segment of data is not available, or the segments of data that were replicated to those 2 historicals are no longer available. So if there's no other copies in the tier, you can get queries that don't have that data and therefore are incorrect. So in order to provide full high availability, you'd have to configure this a little different. Well, this is the recovery from the historical, right? So the historical will, if this failure occurs, the coordinator will ask other historicals in other availability zones to load the segment again. But there's a different way of configuring this that will avoid the hiccup in the query processing. And that's by doing this, right? It's defining a tier that only spans each availability zone. So let's say we want just a hot tier. We can create a single load rule that loads one replica of the segment to each availability zone, right? So because we're defining a tier for hot AZ1, a tier for hot AZ2, and a tier for hot AZ3 that are aligned to the availability zones of the historicals, then we can guarantee that if any availability zone fails, that segment of data is still available. So this is like a higher availability configuration using the Druid's tiering mechanism and the availability zones in conjunction. If you want to configure this kind of availability with hot and cold tiers, then your minimum configuration is going to be with 6 historicals, right? Because you're going to have 1 historical in each of the 3 availability zones for each of the tiers, and you'd have 2 load rules. 1 load rule that applies, like we in our example, 1 month, where it keeps 1 replica of the segment in the hot availability zones. It'll have 1 in each of the availability zones, and then a second load rule with 1 replica per availability zone in the cold tier. So we now have 6 tiers in this configuration. So to summarize, we talked about multiple historical tiers and how you can use them to be more cost efficient, right? So to have the hottest data, the one that's most queried in more expensive servers, so you can deal with higher concurrency and the faster response times that they provide. And colder tiers, where Druid will manage the migration of the segments from one to the other for older data that is typically less queried, so that requires less concurrency and potentially has lower SLAs in terms of performance. We also talked about segment retention rules and how you can define them to migrate the segments by period from one tier to the other, and also to just being queryable from deep storage. And we talked about the overall life of the segment, the life cycle of a segment given a set of rules. So that's what I had prepared for you. So we can start the Q&A. Thank you.